Hello students, I'm your teacher for today, Mrs. Princess G. Mosca Caleja of Santa Rosa National High School. If you are watching this virtual discussion, I want you to comment your name and the time you watch this video so that I can monitor if you already watch it.
Hello everyone, welcome to my class. Everybody listen. Be sure to have your notebook and pen to record the necessary things to be written down in our lesson for today. So this is it. Welcome to General Physics 2. And our lesson for today is all about electric flux. Electric flux is the rate of flow of the electric field through a given surface, or it is the amount of electric field penetrating a surface, and that surface can be open or closed. First, let us take a look of an example of electric flux through an open surface. So, these red lines represent a uniform electric field. We will bring that field a rectangle, which is an open area, and we will divide the area into a very small element, each with a size dA. So, dA is called a differential area. Now, we are going to make the area dA a vector with a magnitude dA. The vector direction is always perpendicular to the small dA. The electric flux that passes through the small area d pi, also called a differential of flux, is defined as a dot product of the magnitude of the electric field E and the magnitude of the vector area dA times the angle between those two vectors theta. The total flux is going to be the integral of d pi, or the integral over the entire area of E dot dA. It is a scalar quantity, and the end result can be a positive or negative. If the flux is going from the inside to the outside, we call that a positive flux. And if it is going from the outside to the inside, that is a negative flux. Again, if the flux is going from the inside to the outside, we call that a positive flux. Very good. If it is going from the outside to the inside, that is a negative flux. Next, we have here electric potential energy. But before that, I have here a jumbled letters, and I want you to arrange the jumbled letters below each item to describe what is being shown in the picture. So we have here 5 images with jumbled letters. So I will give you 1 minute to comment down your answers in the comment box, and let us see if your answers are correct. Okay, time's up. So let us see if your answers are correct. So the first image, okay, so that one is a electric charge. The second one, electric flux. Very good. So third one, we have electric field. The next one, electric force. And the last one is the electric dipole. So did you get it all? Very good. So let's now proceed. So we also have here what we call electric potential. Electric potential is the amount of work needed to move a unit charge from a reference point to a specific point against an electric field. Consider an electric field created by a positively charged Van de Graaff generator. The direction of the electric field is in the direction that a positive test charge would be pushed. In this case, the direction is outward away from the Van de Graaff sphere. So we have here a Van de Graaff sphere. Work would be required to move a positive test charge towards the sphere against the electric field. The greater the charge and the test charge, the greater the repulsive force and the more work that would have to be done and it to move in the same distance. Electric potential standard unit measurement for electric potential is volt. Named after the Italian physicist Alessandro Volta. Since potential energy is measured in joules and charge is measured in coulombs, this means that 1 volt is equal to 1 joule per coulomb. It is also known as the amount of work needed to move a unit charge from a reference point to a specific point against an electric field. Again, measured in joules per coulomb or volts. The familiar term voltage is a common name for potential difference. Keep in mind that whenever a voltage is quoted, it is understood to be a potential difference between 2 points. For example, every battery has 2 terminals, and its voltage is the potential difference between them. More fundamentally, the point you choose to be 0 volt is arbitrary. This is an analogous to the fact that gravitational potential energy has the arbitrary 0, such as sea level or perhaps a lecture hall floor. In summary, the relationship between potential difference or voltage and electrical potential energy is given by V is equal to electric potential energy over charge. Take note, common name for potential difference or electric potential is voltage. And the unit is in voltage. This big letter U, this one is the electric potential energy. Then Q is for charge. The unit for charge is in coulomb. The unit for electric potential energy is in joules. Okay, so we have here decreasing in electric potential and increasing in electric potential or in voltage. So if there is a decreasing in voltage, it means that it moving with the direction of electric field. If there is increasing voltage, means moving against the direction of the electric field. So we have here electric potential energy. Electric potential energy can be defined as the capacity for doing work that arises from position or configuration. In the electrical case, a charge will exert a force or any other charge, and potential energy arises from any collection of charges. For example, if the charge is fixed at some point in space, any other positive charge which is brought close to it will experience a repulsive force and will therefore have potential energy, where K is Coulomb's constant, 9 times 10 raised to 9 Newton meters square per Coulomb square. So, we also have here uniform electric field. So, you can see in the diagram, when Q is positive, this one, when Q is positive, the electric force is parallel to E, electric field. Now, another one, to move Q from B to A, this one from B to A, an external agent must exert a force to overcome the electric force. The third image or diagram, if the charge moves from A, or if the charge moves back from A to B, the system gives up potential energy. So it will become 0. Okay, so let's have an example. Calculating energy. Suppose you have a 12 volts motorcycle battery that can move 5,000 coulomb of charge and a 12-volt car battery that can move 60,000 coulomb of charge. How much energy does each deliver? Assume that the numerical value of each charge is accurate to 3 significant figures. So, assume that the numerical value in each charge is accurate to 3 significant figures. Therefore, we need to convert the charge into 3 significant figures. So, we convert this one into scientific notation. So, let's have first the motorcycle battery. Okay, so we have here the given. This one is for the okay, so let's have first the motor cycle battery. So we have here the given. So for our given, we have here this one 12.0 motorcycle battery that can move 5,000 coulomb. So we have the V, which is equivalent to 12.0 voltage, and the charge, which is equivalent to 5,000 coulomb. But then we need to convert the charge into 3 significant figures. So we will just convert this one into scientific notation. So this will be 5.0 times 10. 1, 2, 3. 5.00 times 10 raised to 3 column. So this will be the value for our charge. So again, so we have voltage, 12.0 voltage, and the charge will be equal to 5.000 times 10 raised to 3 columns. So that will be the given. And unknown, we are unknown with how much energy. So we need to find the energy, the potential difference energy. So U is unknown. So for the formula, we have V is equal to U over Q. We will just cross multiply, so we will be having U is equal to VQ. Then substitute the values for the solution. So we will be having V is equal to 12.0 volts times 5.00 times 10 raised to 3 column. So the answer will be equivalent to, we have, okay, so we will be having 6.00 times 10 raised to 4 joules. So the final answer for the energy of the motorcycle battery is 6.00 times 10 raised to 4 joules. Okay, so next let's have the car battery. So for the car battery, again, same process. We need to find the given. So we have the given for the car battery. We have the voltage, which is equivalent to the 12.0 again, 12.0 voltage. And for the charge, small letter Q, we have 60,000. Then convert that one again to scientific notation. So we'll be having 6.00 times 10 raised to 1, 2, 3 raised to 4 column. Unknown is again the potential energy. So formula, we have U is equal to QV. Then substitute the values for the solution. We will be having 12.0 volts times 6.00 times 10 raised to 4 coulomb. So this will be equivalent to, okay, very good. We have 7.20 times 10 raised to 5 joules. So this will be the answer. So if you're going to write the answer, we have here for the motorcycle. This one is for the car. Our answer for the motorcycle is 6.00 times 10 raised to 4 joules. And for the car, we have 7.20 times 10 raised to 5 joules. So, while the voltage and energy are related, they are not the same thing. The voltages of the batteries are identical. Both of them have 12 volts, but the energy supplied by each is quite different, as you can see. Also, take note that as a battery is discharged, some of its energy is used internally and its terminal voltage drops, such as when headlights dim because of a low car battery. The energy supplied by the battery is still calculated as in this example, but not all the energy is available for external use. Note that the energies calculated in the previous example are absolute values. The change in potential energy for the battery is negative since it loses energy. These batteries, like many electrical systems, actually move negative charge, electrons in particular. The batteries repel electrons from their negative terminals through whatever circuitry is involved and attract them to their positive terminals. Another one, we have here what we call point charge. Point charge, the electric potential at a distance R from a single point charge Q can be delivered or derived from the expression of its electric field. So E is equal to KQ over R squared. The result is V is equal to KQ over R. So superposition of electric potential. The electric potential L, or at point L, is the sum of voltages from each point charge scalar. So we have here point L. So if you're going to get the electric potential of point L, you need to add all the voltages from each point charge, which are scalars. So example is this one. Consider three charges, Q1, Q2, Q3. The electric potential due to this charge at any given point is the sum of the electric potentials of all the charges. So V is equal to V1, V2, V3. Meaning if you're going to get the total electric potential, you need to add all the electric potentials present in the given charges. So this will be a sample formula. Okay, to make it clear, so we have here different formulas or different terms to consider for you to not be confused in using those formulas. So we have here the Coulomb constant. K is equal to 9.0 times 10 raised to 9 Newton meter square per Coulomb square. For the superposition of electric potential, this will be the summation of all the different electric potential. Change in electric potential energy. We also have electric potential, then electric potential energy. So let's have here an example. A point charge of negative 6 times 10 raised to negative 9 coulomb is 3 meter from a point A and 5 meter from point B. Find the potential at point A and point B. What is the potential difference between points A and B? So we have here the given. And our unknown is we're going to find the potential difference between point A and B. So what formula are we going to use? Okay, so the formula that we are going to use is the superposition. Okay, so we have here V. Okay, we have here V is equal to the summation, or K, the summation of Q over R. Okay, again, I will write it. So, V is equal to K, the summation of Q over R. So, you need to sum up the potential difference between A and B. So, let's answer. Let us start with letter A first. Oh, both of them. Okay, so for the solution, so we have B is equal to we have K 9.0 times 10 raised to 9 Newton meter square coulomb square times we have A, we have negative 6.00 times 10 negative 9 coulomb divided by 3 meter. Okay, this one is number 1. Then we need to add hindi kasha. Wait. divided by 3 meter, 3.00 meter. You need to complete all the units. That one, then plus letter B. So again, Q or K, we have 9.0 times 10 raised to 9 Newton meter square per column square times, I will just write it like this, negative 6.00 times 10 negative 9 column divided by 5.00 meter. Okay, then this will be equivalent, this one will be equivalent to negative 18 the other one will be equivalent to plus negative 10.8. So this will be equivalent to negative 28.8, negative 28.8, the unit for electric potential volts. Okay, or joules per coulomb. Why joules per coulomb? You cancel meter and meter, so you only remain with meter, Newton, meter, and you cancel coulomb and coulomb. So, isa na lang yung coulomb per coulomb. So, this will be equivalent to volts. Okay, so that one is our example number 1. By the way, since it is negative, the answer is negative, meaning decrease in voltage means moving towards the direction of the electric field. Okay, another example, example number 2. So, two charges, Q1 is positive 3.5 nanocoulomb. The other one is negative 5.3 nanocoulomb, which are separated by 10 centimeter. Calculate the electric potential. So, first is that we need to find the given. So, for our given, we have here Q1, which is equivalent to positive 3.5 times 10 negative 9 coulomb. So, R, or the distance for R1 from point B is 4 centimeter. 4 centimeter. Then next we have Q2, which is equivalent to negative 5.3 times 10 negative 9 coulomb, and R2 will be equivalent to, because we're going to find the electric potential at B, so we need to add 4 plus 6 plus 4. So this will be equivalent to 14 centimeter. So our unknown is V at point B or point B. Okay, that one. So the formula that we are going to use will be, we have a potential difference at point B is equivalent to KQ1 over R1 plus KQ2 over R2. But then, take note that in our R, we need to use a standard unit, which is in meter. But in our given, this one is not yet in meter. So, all we need to do is we need to convert R1 and R2 into meter. So, 4 centimeter, convert it to 100. This will be equivalent to 0.04 meter. The next one, we have 14 centimeter. This will be equivalent to 0.14 meter. So, let's proceed now. We substitute the given values. We have 9 times 10 raised to 9 Newton meter is square per coulomb is square. Multiply it by 3.5 times 10 raised to negative 9 coulomb. Why? Kasi this 1 negative 9 is nano. Okay, so plus we have 9. Okay, this one is divided by 0.04 meter. Next, we have 9 times 10 raised to 9 Newton meter is square for coulomb square times 4 or negative 5.3 times 10 negative 9 coulomb divided by 0.14 meter. So, V is equivalent to, yung nasa taas, this will be equivalent to 787.5 voltage plus negative plus negative 340.7 voltage. So, you add B is equivalent to 446.3 voltage. So that will be the final answer, 446.3 voltage. So another example, a charge of Q is equivalent to 5.3 nanocoulomb is accelerated from the rest through a potential difference 0.25. What is the change in potential energy of the charge? So again, we have V, the first formula, V U over Q. Okay, so we have here the given, or I will just write here. the given. So we have Q is equivalent to negative 5.3 times 10 negative 9 coulomb. And we have the potential, which is equivalent to 25 volts. Then for unknown, we have U, or this one is the electric potential energy. Then U is equal to QV. Substitute it, negative 5.3 times 10 raised to negative 9 coulomb times 25 volts. So this will be equivalent to negative 1.35 times 10 negative 7 joules. So this will be the answer for electric potential energy. Okay, so for today's lesson, we've discussed electric potential difference, electric flux, superposition. Okay, so for your performance task, make a poster slogan that would explain your answer about the valuing part at the next slide. This one, valuing. We have all observed the awe-inspiring beauty and power of a good electrical storm. The flashes of lightning, followed at varying time intervals by a clash of thunder, can be both fascinating and frightening. What is lightning? How are thunderclouds capable of producing the impressive electrical discharge that we see? What happens in an electrical storm? So you need to make a poster slogan out of this valuing part. Okay, so comment down your reflection, the date and time you watch this video discussion, and hope you learn well. Goodbye. See you again next week.